Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great pleasure and an immense honor to introduce this tutorial today and to chair it. This is going to be a joint tutorial with Julia Pearl and also Elias Barenboim. I have written some notes that I'm going to read because my memory is not that great. So Elias is a PhD student at UCLA with Julia, and he's received in 2012 the Yahoo Key Scientist Challenges Award, and then very recently he's received the Dissertation of the Year Fellowship from UCLA. The rest of the introduction focuses on Julia. So I think it's fair to say that Julia Pearl is one of the fathers of modern artificial intelligence, of modern machine learning, and of modern cognitive science. He's pioneered the application of probabilistic methods to the understanding of intelligence systems, whether natural or artificial. One of his key contributions is the development of graphical models, and in particular of Bayesian networks, as well as the fundamental algorithms for inference in these models. Graphical models have had a transformative impact across many disciplines, from statistics and machine learning to artificial intelligence, and they are the foundation of the recent emergence of Bayesian cognitive science. I'm sure you all own the book. In 1988, Julia published a book entitled Probabilistic Reasoning in Intelligent Systems that summarizes all of his work in probabilistic reasoning and graphical models. But that's only one part of it, right? More recently, Julia further developed his work on graphical models to address one of the deepest challenges in philosophy and science, the analysis of causality, which is what we're going to hear about today. Julia developed a calculus for reasoning about the causal structure of the world, and he's able to interpret graphical models as providing a specification of the causal structure of the system, rather than merely providing a compact representation of a joint probability distribution. I'm sure you also own the other book. In 2000, Julia published his seminal work, Causality, Models, Reasoning, and Inference, where he lays out a complete framework for causal discovery, interventional analysis, and counterfactual reasoning. What you may or may not know is that prior to his work on probabilistic reasoning and causality, Julia made seminal contributions to artificial intelligence, especially in search and heuristics. And there comes a third book, which you may or may not own, the 1984 book entitled Heuristics, Intelligent Search Strategies for Computer Problem Solving. Julia has won a lot of awards, and I'm only going to mention 3 of them, which coincidentally were all awarded on the same year, in 2011. He was awarded the Turing Award, which, as you all know, is the Nobel Prize of Computer Science. He also was awarded the Technion Harvey Prize in 2011, and he also won the Rumelhart Prize the same year, which is probably the Nobel Prize of Machine Learning and Cognitive Science. I'm going to close with a fun fact. One thing you may not know is that there is a Wikipedia page about the Pearl vortex. So the Pearl vortex is a particular type of supercurrent that happens in a thin film of type 2 superconductor. And the reason this exists, this Wikipedia article, is that Julia did his thesis in electrical engineering, and he actually worked on, well, I'll just read the title of his thesis, was Vortex Theory of Superconductive Memories. Luckily, he got interested in intelligence and probabilistic reasoning, and so that's what we're going to hear about today. So that's for the introduction. Now, the rules of the game are this. We have 2 hours. I asked Julia whether he was planning to make a break. He said no. You guys should be able to cope with 2 hours of tutorials. I think that's fine. However, he said he will not feel insulted if you leave the room to take a short break, so I think that's fine. The other thing is, although we're going until 11:30, We don't have to vacate the room at 11:30, so I think the deal is we're going to open it for questions at 11:30, and Julia said that he's happy to be here all day answering questions. So I think I've talked way more than I should. I'd like to introduce Julia and Elias, and let's also thank them for coming and talking to us.
Thanks for the introduction.
You can use this guy or the handheld one.
Thanks for the introduction, and I'm so happy to see so many people here registering for this tutorial. I think you made the right decision to come here. Despite the fact that causality is not in the mainstream machine learning or NIPS, I counted only 3 papers with causality in their title. But I don't know who is behind the time, NIPS or I. But the reason that you made the right decision is because I'm going to try to impress you that you need to go through some paradigm shift from the way most people think in machine learning and in NIPS. And the paradigm shift will be from statistical exercise to something different, which I'm going to call causal inference. And I'm going to summarize that then in 2 fundamental laws of causal inference. Once you have it, you can derive everything that we are going to talk today. But I'm going to dwell on that, and I'm going to take half hour to dwell on these 2 yellow topics, even though they're trivial, because every time I leave the room and people say goodbye, it was very nice, they forget it. And they keep on doing the old statistical stuff. And then we're going to talk about tools, because this is the litmus test of understanding. If you have a bunch of tools like addition and multiplication and you can do arithmetic, then you understand arithmetics. And if you just know the piano axioms, that's not enough. So we are going to, Elias is going to take over at the basic tools and introduce graph separation, truncated product formula, the backdoor adjustment formula, and the do calculus. Now, I need to know something about your background. So I'm going to take 2 seconds and ask, how many know this separation? Good. That's 50%. Elias, you got supporting audience. And truncated product formula? Because that indeed is a transition between probabilistic Bayesian network and causal Bayesian network. So we know where we have to spend our time. And then capabilities. That's just to summarize and to show you that all these tools have some applications and very, very, very successful application. By very successful, I mean I consider it to be a triumph of science, and I'm not exaggerating. Things that lingered on for years, maybe centuries, okay? Pressing problems got solved. So with all these promises, I'll start. First, the fundamental shift. This is statistics proper. And it was also machine learning proper. From what I learned by looking at some of the literature here, the idea is that machine learning is an attempt to find a useful representation for the data. That data-driven. If you find a good model for the data, then you have accomplished machine learning. This is not the paradigm that I'm going to talk about now. This has been 150 years of statistical tradition. We have to quit that because we are dealing with modeling reality and not with modeling data. This is what causal reasoning is all about. So the exercise goes someplace behind the curtain. There is a Santa Claus called joint probability distribution. When this Santa Claus is gracious, he or she spits some data at us, and we look at the data, and we have to, and our task is to infer some useful properties of the Santa Claus, of the oracle. Estimate the mean, or estimate whether a customer brought product A would also buy product B. Many people are making good money on that. And it is in a statistical task. It is a relatively easy task, at least because you have an expression for it. Here it is. It is, the query is the probability of B, it's an event of buying a product, given the event of buying product A. Okay? You have a mathematical expression for that. You're on your way. What happens in causal reasoning is something different. Bing, I want to estimate the probability of the sales if we double the price. Today I wake up and today I become greedy and today I want to double the price. What will be the sale? I'm going to introduce an intervention, doubling the price. It's a new probability. I'm going to create a new probability because I'm going to change the whole mechanics, although the price fluctuated in the past and maybe reached doubling what it is today. But the reason it reached could have been other many things, like inflation, a competitor got out of business, and all kind of things. Today I want, with the current condition, which I don't know, I want to double the price. I'm changing the probability distribution and I fix the price at double what it was. Or something which, a question which is more applicable. Estimate the probability of cancer if we ban smoking. So everybody is going to ban smoking. It's called a P prime. It's a different kind of anatomy here. Because, and it's not equal to the probability of cancer given that someone in this population of non-smokers. It's not. Because if you ban cigarette on anybody, so you ban cigarette also for those who currently are smoking. So you bring into the consideration units that previously were not there. Not only the non-smoker, but those who currently smoke, you bring them in. So that's first thing. What do we know about the new probability? Number one, we know that P prime has a property that the price is double. Okay? Beautiful. But what else? Certain things remain invariant, other things change when we do that. So who is the guy to decide what remains invariant and what is to be changed? We talked already that the probability, its conditioning will not do it. Because conditioning is a selective operator, a filter. You only look at one subpopulation. Here we are doing it to everybody. So it's a different operator. Doubling the price is not equal to seeing the price doubled on its own without intervention. Therefore, we are looking for some mathematical oracle that will take the probability distribution and will calculate what ought to be changed and will generate a new probability distribution whose properties we are interested in estimating. And P, unfortunately, doesn't tell us how it ought to change. P was a very generous and powerful oracle when we talked about seeing. We know how P changes when we condition on any event which is part of the model. That's beautiful, very powerful. And that is why people got hooked to the operator which is called Bayesian conditioning. Okay? Because the probability itself tells you how it ought to, how the belief ought to change when you see something. Okay? That's very powerful. You don't need more than P. Now we are talking about interventions, and P doesn't contain that wisdom to tell us how it ought to change. If you intervene and you change something about it, maybe it's conditional probability or maybe some other trick. Okay, and that's why it is so hard to abandon this oracle. It's a painful operation. That's why we got conditioned, I would say even obsessed, with the habit of conditioning, even though it is harmful. And it has been harmful, and I blame the Bayesian conditioning operator for many, many blunders in the 20th century. I can go over the list, blunder after blunder. The whole confusion between regression and structural equation is a result of that obsession. But I don't blame the people who got into a habit. It's a powerful operator, and probability theory doesn't offer us an alternative. So naturally, if you want to fix something, you condition on it. It's so natural. No more. Because sometimes you have to distinguish between seeing and doing, and this is what causality is all about. So, Bing. That's only one reason to deal with intervention. The other one is to deal with counterfactual. For instance, you want to estimate the probability that the customer who bought A would buy A if we were to double the price. So you go back in time and you say this particular customer, had we doubled the price in 2005, he would have bought product B. Why do you want to reason backward? We are all pragmatic, right? We want to go only forward. Regret has no place. Regret has place. Because due to regret, agents learn about what piece of software they have to change in their mind when they fail. So regret is very important element here. Now, we are coming to a new era where we replace the old oracle with a new oracle, which I call data generating model, who does two jobs. Number one, decide what ought to change in the probability and how to. And now what we are seeking is the aspect of the data generating model and not of the joint probability. Okay? And what is it? It's an invariant strategy, sometimes called mechanism, recipe, law, protocol. Statisticians had a very hard time to give it names, so they invented it. It's just the structural equations with an invariant strategy by which nature assigns values, not probabilities, values to the variables in the analysis. So I conclude the first bullet by saying the difference between the two is that P is a model of data and M is model of reality. And we are in the business of modeling reality. What kind of question should the new oracle answer? We already looked at them. Observational question. What if we see A? That's easy. That's statistics. That's Bayesian network. Okay. Action question. What if we do A? A being a proposition. A counterfactual question. What if we did things differently? And if you want to decorate it with probability, you can ask all this question, what is the likelihood that, what will happen, how likely things to happen if we see, if we do, if we had acted differently. And it's interesting that this form a hierarchy. Hierarchy in the sense that we have in a language, we have names for those, but the hierarchy means that if you cannot get conclusion at layer I unless you have assumptions in layer I or higher. We have syntactic distinction, but most important is to notice that we have representation for them. If you want only observational queries, you can handle it with Bayesian network. If you want action questions, interventions, you should use something like causal Bayesian networks, which are defined in my book, page 24. And and if you want to go deeper, and that's counterfactual question, causal Bayesian network will not do it for you. You have to go to functional causal diagram structural equations. The defining ingredient is that the model tells you what caused a value of each variable to be what it is. Okay? It's value driven and not probability driven. Okay, it's very important to go back and look at the literature on which you were brought up. And you and I were brought up on this literature. It has all kinds of concepts. Some of them are causal and some of them are statistical. And the distinction is very crisp and easy to master. It's one, I can say it in 5 words. Okay? Every concept that can be defined in terms of a joint probability of observed variables is statistical. And every concept that cannot be defined, I call causal. Easy? Let's look at something. We all know how to define all those. Even range of causality, okay? It's defined in terms of a probability. Therefore, it's not causal. And Clive confessed to me. There's nothing causal about my range of causality. Propensity score, you can find that to be sort of a trick in causal reasoning. It's defined in terms of the probability of a treatment given some covariance. Since it is defined in probabilistic time, forget it. It belongs to the statistical side. I just give you one example here. Randomization. Something that you find in this chapter number 2 in every statistics textbook, right? Is this a statistical concept? Most statisticians will say yes, we learned it in chapter 2. Right? The answer is no. Because you cannot define randomization in terms of, I repeat, joint probability of observed variable. If I give you a bivariate normal and I tell you that if one of the 2 variables is randomized, you cannot tell me which. Therefore, it is not statistical. It's counterfactual, it's causal, and therefore randomization gives you answers to causal queries. Without it, okay. It's extremely important. Keep it in your mind because I'm going to repeat it, and I know that next reviewer among you is going to say, I cannot see why instrumental variable is not causal, is causal and not statistical. Well, this is why. Because it cannot be defined in terms of joint distribution of observed variables. You can invent all kinds of latent variables, okay, and play all the tricks with latent variables. For instance, I can invent Cinderella's hair color. It's a nice latent variable. Or I can, moreover, I can invent a latent variable which is called the answer to my research query. How is that? Does it make my problem statistical? Just because the true answer lies in the probability that my answer is equal to 5. Okay? So just because I can cast it in terms of joint distributions of variables, some of them are latent, doesn't make the problem statistical. And because of the hierarchy, and because the layers are more or less isolated, very little leakage between them, we have Cartwright's famous slogan, no causes in, no causes out, which means that if previously you were or we were accustomed to look at problems in terms of here's data, find conclusion, the game is going to change now. Here we have data, and we have causal assumptions get the causal conclusion. Without the causal assumption, you can't. Or replacing causal assumption will be a result of experiments. Experiments with intervention, fine. Together with causal assumption and together with observational data, you can get causal conclusion, and that is the kind of exercise we are going to be dealing here today. And another thing to realize is that If causal concept cannot be defined in terms of joint distributions, therefore you need new mathematics. You cannot express those assumptions which are required to get causal conclusion. You cannot express them even if you are willing to accept those assumptions which are untestable. Right? You are willing to accept them. You cannot express them in the traditional language of statistics. So you must have a new mathematics. This hurdle and this mental barrier is even more traumatic to overcome than the idea that you need to have assumptions. The fact that you need new language, statisticians will go to war and will not accept it. And even if they accept it in the form of an old language, such as potential outcome. Okay? So everything is okay. I just invented a new variable called y sub x. Here it is. So it's a new latent variable that I cannot see. And now everything is statistics. So I'm back home, but I wouldn't change the language. Okay? I'm willing to invent all kind of crazy latent variables, but I wouldn't change the language in which the Bayes conditioning is the dominant conditioning. Okay. But in the 1920s, somebody already realized that you need a new language. This was Civil Wright, a geneticist, and he said, let's put as equations, structural equation, okay? Like F is equal to MA and all this, just the physical equations. If you think that the color of the guinea pig is going to be red and what you feed it and the gestation period is affecting our factors that determine the color of the baby guinea pig, so let's write an equation. Those equations turn out to be called structural because they are not regressional and because they are not part of statistics proper. Okay, let's go there, and this is my generalization of what I told you. This is our new oracle. The world as a collection of springs. Every variable gets its value according to some function of other variables and some background factors, which we call exogenous, because we don't insist on explaining them. Some of them are measured, some of them are not, but this is our oracle now. And here's an example that you're all familiar with, but this is not regression. It tells you that nature, in order to determine the value of y, Lady Nature consults the value of x and uy and alpha, and then decide how to combine them here linearly, but it can be non-linearly, and decide on the value that y obtains. This is a huge simulator. Nature is waiting for the values here at v to be determined, and then takes that and determine the value of vi. It also admits cycles, as long as you have this deterministic relation there. And you can assign probabilities to the exogenous variables, and once you assign that, then the probability of u, together with the deterministic functions here, induce a distribution PV over the observables. Okay? So this is our new oracle. And we demand that this oracle will answer all queries, observational, interventional, and counterfactual. And indeed it does. It's so easy. Embarrassingly simple to define counterfactual in that business. Okay, if I want to say that to define the potential outcome or y sub x u, which means what the value of y had x been small x for particular unit u, particular vector of characteristic u, it's very easy to compute. I go to my structural equation. Here x was determined by u and y by both x and u. And now I'm going to mutilate the model and say, no, x, you ought to be a constant. I replace the equation by a constant, and now I have a new model from which I can compute the value of y. This is the definition of counterfactual. Easily computable by every high school student. Unfortunately, the textbooks on structural equation, the textbooks, I haven't seen any textbook where you have a homework saying compute the counterfactual, compute the probability that a student named Joe will get a score of 25 in the example had we doubled his homework or had we introduced him to this program. It's not existing, but this is so simple. Okay, I convince you that it's simple. I convince you, because it's just high school. Now that I convince you, I will not convince you that all interventional problems can be answered in the same way. In the same way, suppose I want to I ask the question, what will be the probability of y given that I do x? I intervene. Go to your model, intervene, namely overrule the current influences on x, overrule them under the power of your muscle because you're going to do something, and force x to get the value x. You have a new model with a missing arrow, easier to solve. Find the probability of y in this model, you got it made. This is the answer to the intervention. Easy, right? Good. We are making progress. Yeah. So here you have already the how to compute interventions, and I'll show you how to compute it. Very easy. If here the joint probability of x, y, u was the product according to like Bayesian network, okay, is conditional probability of son given its parent, being. Now we are cutting off this factor, being. All you have is that, and the answer to our query is just the two factors that remain. If you want just the probability of y, okay, that's called truncated product. If you want the probability of y, not of u, you have to sum over u. And then you have what is called adjustment formula, adjust for u. If u is unobserved, Elias is going to talk about it. But now we come to the two fundamental laws of causal inference, and I put them again. One is the amazing fact that you can compute easily all counterfactuals and interventions from a mutilated model, from a structural model M, once you mutilate it accordingly. The second one is that you have a law of conditional independence, this separation, namely that the graph that describes the structural model, just telling you who is the parent of whom, that graph contains the answer or had a signature of the original model and allows you to infer some constraints in the observed distribution. That's this separation, since most of you know it, I wouldn't elaborate and just call it a miracle because it is such powerful theorem. It allows you to look at separations in the graph and infer the structure of the model, of the Santa Claus behind the data. That's to show how it works. This is how the model looks like, collection of functions. Every variable is a function of the other, non-linear function. We don't know the functions. And we know that we're never going to find the functions. We admit it and we confess it and we resign to it. Okay? But now we can do so many marvelous things under this state of ignorance. And it says that if the U's are independent, you see those U's? If they are independent, then the observed distribution P of all the variables here satisfies the constraints that are, one, independent of the function f here, and then the probability we assign to the U's, as long as they are independent, and they are readable from the graph. So here is a missing link. Okay, you have separation. Here you have a missing link, separation. And these are the conditional independencies that are implied by those separations. The applications, one, model testing. You can test the model by those implications. They are observable, right? Structural learning. Reduce what if I do questions to symbolic calculus, which Elias is going to show, and reduce scientific questions, including counterfactual, to causal calculus. Elias, the stage is yours. Basic tools.
Thank you. It's nice to be here. I'll talk about layer number 1 and number 2. A warning: layer number 1 can be, as you I already discussed, but can be taken by itself alone. And I think this was the historical sense what happened. We didn't know about the other layers. Then you can. Some people ignore completely layer 2 and layer 3. And this is totally fine, as he said, if you are interested to analyze and to ask queries about probabilities. If you want to probability of evidence, probability of Y given E, or map, or MPE, or queries like that. We take a different approach here, and I'll try to show what does it mean, what he's talking about when he says that the layer, some model in layer number 3, a structural model, generates a distribution in the first layer. And this is part of his picture. He has the data generating model. He has the joint distribution behind the data generating model, the joint distribution after it, the generating it, and then you have data. And then this is the result that connects them. There is this theorem by Pearl and Verma from 1991 saying that every Markovian structural causal model, M, recursive meaning acyclic, with independent disturbance, the U terms of the exogenous variables that he said are independent so far, induces a passive distribution P of V1, V2, Vn, this means over the observables, that can be factorized with the famous or the product that we are used to. Probability of V1, V2, Vn, factorizing the family wave V1 given the Vi given the parents, where PA of A are the values of the parents in the causal diagram associated to M. And the causal diagram, he has his picture showing the graph, and the causal diagram, you can go from one to another. The diagram is just encoding the argument of the functions that he said. It's just a nice way to depict it, what are the arguments. I'd like to talk about the graph separation, because this distribution and this kind of factorizations imprint some marks that are known as condition independence. People are already familiar with that. And condition independence are basically symmetries that you have in the distribution. X is independent of Y given Z, meaning that you compute the value of X. If I know the value of Z, the value of Y is irrelevant. This is what it says condition independence. And you like to understand, to see what this means. Then it seems that a lot of people know this separation. Then I will go fast on that. But basically, I like the metaphor due to Richard Chines from CMU, that he considered the graph as a plumbing system. And in this graph, between pairs of variables, you have all these pipes, and between the pipes, you have flow of information between them going there. And you have different kind of valve. The valves can be open or closed. And you have two different types of valve. You have the normal valve, and you have abnormal valve. The normal valve could be this one is known as common cause, the first one in your left side, that you have Z pointing to X and to Y. Z could be the parents of two children, and X will be the children. Then the DNA of the children is independent of the other one, or the child is independent of the other one, given that you know the DNA of the parents. This is the common cause pattern. And the other two is basically chains, X pointing to Z, Z to Y, or the reverse chain. This is a Markov of order 1, chain if you want of order 1, to compute the weather today. The weather from 2 days ago is in the weather today is independent of the weather 2 days ago if you know the weather from yesterday. This is what you have here. This is the normal valve. And then you have the abnormal one. The normal valve, there is the flow going from X to Y. And then when you condition in the valve in the middle, you close this flow. This is the idea. And then you have the abnormal valve. That is, you have the X and Y pointing to Z, these convergent arrows. The X could be an independent coin, the fair coin. The Y could be another independent fair coin. When Z could be, in the classical example, I think it's due to Yuda, you have a bell. And the protocol, if you listen, the bell will ring if and only if the two coins are the same. Then suppose that one of the coins is heads. What's the probability of I listen the bell ringing, what's the probability of the other coin being heads? It's probability 1. Then you kind of entangle or you create a correlation between two variables that are independent in the universe. And this is the pattern related to selection or some sort of filtering. And then you have the descendant of the collider that is acting, this W here, that act almost as the collider. And the idea here that they are independent, and then you condition, then the flow is passing there, the flow of information. I just would like to go through some example, given that Half is not familiar with that. You have the classical graph when you have season, sprinkler, rain, wetness, and slippery. Just a second. And slippery. And then you are trying to judge statements in the kind of, is condition independence 1? Is wet independence of sprinkler? The criterion is, I didn't say, sorry. The criterion is between two pair of variables. They are independent if all paths between them are blocked. And then in this case, wet is independent of sprinkler. This is the corner case, but there is even an edge between them. Then there is flow of information going from sprinkler to wet and wet to sprinkler. If you're not in the causal sense, then they are not independent. This is a trivial example. And then I have another one. Is wet independent of season given sprinkler? And then if you try to apply the valves, you have the season, sprinkler, and wet here. This matches a chain. That is this first pattern here. When I condition the guy in the middle, that is the sprinkler, the Z, in the case, I block the flow of information that is going through this guy. Then you have this path blocked. Are they independent? You have to check all paths between them. Then there is the season, rain, and wet. That is another chain. If I don't condition the guy in the middle, there is information passing there, and then they are not independent. And this is kind of judgment that we are trying to make. Another one, is rain independent of slippery? Rain is independent of slippery on the bottom, given wetness. We have, again, a chain here, rain, wetness, and slippery, that is blocked, given that you are conditioning the guy in the middle. And you have this other path here, rain, season, sprinkler, sprinkler, wet, wet, slippery. It's blocked too because this is a chain. Then you block both paths, and then finally they are independent. And then you can go on, let me skip one. And you have sprinkler is independent of rain, given season and wet. Sprinkler is independent of rain, given season and wet. This is the question. Sprinkler, season, and rain form a common cause, right? Season pointing to sprinkler, season pointing to rain. Then when you condition in the common cause, you are blocking the flow that is passing through here. But here you have a different pattern. You have sprinkler and wet, sprinkler and rain pointing to wetness. And then you have a convergent arrow. This is a collider. When you condition on wet, you are opening this path here. Then they are not independent. And this is the kind of judgment that we want. The idea is that separation in the graph implies separation in this distribution. There is this marks imprinted there. What's important to say, I think this is just encoding, is some sort, the condition independence in the graph is a sort of basis to encode a system, a probabilistic system, or a probability distribution. There is an economical way or parsimonious way of encoding that. Even that the intuition, if you're just thinking about layer one, even just layer one and ignoring the other layers, you have the intuition in the causal sense, but there is no causality there. But our goal is to go to the causal layer. Then this was just a brief review. And the second layer is the causal hierarchy. We want to reason with causal effects, or what if we do, or if I do X is equal to X. And why you want that? If you see the news, we're embedded in news in the kind, study heavy coffee drinking people under 55 linked to this keyword to early death. Then it seems to be bad to drink coffee. And then you have other news that talk about relationship of coffee consumption and with mortality. And every 3 years, we have the flip of the conclusion of the study, saying that you should or not do something. And it's kind of tough to us because we need to reason with causal knowledge. And we have something more serious. Alcohol causes 20,000 cancer deaths in the US annually. Then it's kind of, for someone that likes to drink, this is a bad news. But then you have something not so bad, say 1 drink of red wine or alcohol is relaxing to circulation, but perhaps 2 is too much. It can be stressful. It seems that there is some sort of threshold here, but then you can go for a happy news saying, why do heavy drinkers outlive non-drinkers? Then it's a good one, good news, right? There is light on the tunnel. Then we would like to understand, and then you can go on and on about the grapefruit that can be good or bad. This one is a very important journal, New England Journal of Medicine, talking about nut consumption. Some people make it as a joke, but this is and I like to, but this is kind of important because people take their decisions in their lives and use these results as basis to change their habits and their behavior. And you can kind of feel the struggling that Yuda is trying to pass in terms of methodology of how to get these results. And this is kind of our goal here. I just refresh, given that I talk about layer 1, his picture, he has this causal inference, and I use the expression, this is due to Phil David from Cambridge, moving between regimes. And then you have a population that is flowing naturally in your natural regime P, and then you have a distribution P prime. I would like to give a zoom on that. This is why I'm talking about this, because it's a very important point. And I have a distribution 1, P, that is a regime 1 that is in the natural flow. People is smoking because they have peer pressure, or because they have some DNA, or because there is a culture, or etc. It's flowing with their, perhaps free will if you want. It's a more tricky question, but it's flowing. And then you have some kind of abrupt change, someone put their hands in the system and force some change. Do an intervention. Then how the system will react. Are you breaking the system completely or not? Or how it relates with the other system? And his question is whether less people would get cancer if you ban smoking. This will be the kind of question. Just to bold notes, putting emphasis observation 1, he said the distribution alone tells us nothing about the change. It describes static condition in a population under a specific regime. It's just a picture of how the natural flow is going. Naturally, what we want is we need some way to represent this idea of change. I'm not Obama trying to sell the political agenda, but you for Americans perhaps understand, but we need to represent this idea of change and how the population reacts when it undergoes this thing. Note, I just want to step back, but in terms of machine learning, you have a very tough generalization problem and stats, because you collect and have samples over this P. This is the distribution P. And then you have plenty of samples. All theory that you have are statistical methodology, not for people in other empirical fields that's just plugging in and doing regression. But here you are trying to understand it's different. But these methods, they are trying to give us a guarantee. There is some kind of true underlying truth that you would like to convert to that. Or a number, or a distribution, depending on your political perspective. But there is some truth that you are trying to get. And you are kind of, you have samples. And you would like to have the feeling that if you're accumulating samples, you are approaching this truth, right, in the universe. But here you have plenty of samples, and these guys who have 0 samples. Then how can you generalize or apply methods that are relying strongly on samples in something that you don't have samples? This is kind of very tough generalization problem. And you need some way to relate these two guys, the P and P prime, or these 2 different regimes. How they are connected. Then this is the zoom in on the picture that I promised. The ARP, I'm calling the big picture the challenge of causal inference. And you have this real world, and then I'm putting a graph here. X could be the treatment or the decision. Y would be the outcome. X could be take or not the drug, or enroll in a certain program or not, or getting a training, or smoking or not, some decision or action. Y would be the outcome, survival after 3 years of treatment of the drug of cancer, of earnings after 10 years of training program. This is some sort of outcome, and you have line between them a W, you call mediator, could be a biomarker or something like that. And then you have a Z that is as a vector, could be a high dimensional vector that is affecting X and Y, it's changing X and Y. And Z could be age, sex, ethnicity, culture, peer pressure, socioeconomic status, and etc. Could be plenty of variables that are affecting these guys. Our reality is this one, and when the guy decides to take or not the drug, he's listening to this age. The decision, there is a function here, x is equal to f of z, and this is what makes the decision. This is our reality. And then we want to reason, there is this change, and we want to reason about the alternative world. When this rule, the original rule that he said, is no longer valid. You are kind of overwriting this rule. And then you don't have this edge from z to x. And the question, how these guys are related. You could ask, you don't have time, then I'm speaking more fast and cannot interact so much, but the natural question, how this is related with causality, and the relation is obvious. Our goal, what causality is asking, is how much y changes with x if you vary x between two different constants this is free from the influence of z. Then somehow you want to grab x with our hands and keep swinging or change or wiggling that and see how y reacts. In the natural world, in this one, in your left side, x is changing also with z. Z and x and y are changing with z together. In our reality, we want to grab x and swing and see what is happening with y, independent of the z. And this is kind of the key, and is the intuitive definition of causal effect that everyone agrees or believes on that. Then this is the trouble. We have a distribution, we're collecting data over z, x, w, and y, a passive distribution, and we would like to make a claim about a different reality. We did this ban smoke before in our lives. Then how can you claim about this guy that is have a different signature, a different name, y given to x? A classical example that pops out this kind of thing, or the difference between them, is due to Fisher. That he said, suppose that your action here is smoking. Suppose that, let's ignore w for now. X is smoking or not, y is getting cancer, and z, he claims, this is about on 60s or around that, he claimed that there is a genotype that at the time it couldn't be measured, and the genotype is affecting the x and y in the following way. There is some strata of the population, and this strata of these people with this genotype, they are smoking, this is making them to crave for nicotine, and they will smoke, and the same z is making these people to die. Then in this strata. Then he claims that even that you are seeing x and y correlated, and strongly correlated, the z, the influence from z that is passing through these paths here, that is in the back, is not going through the front, is the one that is explaining the correlation. If you go to reality and try to wriggle x and check the difference between smoking and not smoking, the effect will be zero in this population, or very small in this population, because the explanation is through the z. Then you have a methodological struggle, because you connect data over here, but you want to make a claim here. And then his was the way that he tried to defend why smoking was not bad. This was the goal, and technically he was correct at this point. And you should give credit for him for other reasons more than that, but I will explain. There is a struggle. Then you could ask, what's the solution? How can I get the answer for this one? As Yuda mentioned, there is a solution, a method for computing causal effects that is these randomized experiments. And this was the trick, is due to the same Fisher, but the first part of the century, about 1920s, or around that. And then you have real world, and you have change, and this is what you want. And then his trick was the following. Let's create a microcosmos, or a micro world, that you try to mimic the condition that we want. And the procedure is in 2 steps. First is ordinary or normal. You just do a random sample of your population. Then after that, you have a coin. If you have binary or a die, if you have multiple levels, but let's stick with the coin that is the simplest. And then you flip the coin. If the coins give the answer 0, you send the people to a room and say, no, you don't take the treatment. If the coin is 1, landed 1, then you send to another room and you make them to smoke or to get the treatment in the case. Then the person doesn't have option. The key here of this diagram, or in pictorial way, somehow you are neutralizing the effect of z on x. Note that I don't know if it's possible to see, but I put in a kind of gray, kind of different shade here, so in the z to x you are be able to neutralize. Then the original effect that people will smoke for the genotype or peer pressure is no longer an option. Now the coin is the one that is deciding who is smoke or is not smoking. Then this is very beautiful, and even I think is the way that the graphs pop out exactly what we want. For sure, also we couldn't submit the population to smoking and then later to non-smoking, because then it would be another population. Then it's completely impossible to do that physically. Then it's some kind of low-level counterfactual or layer 1 counterfactual. But this was the trick. It's a beautiful method. The challenge, then this is, the output of this room x0 is probability of y given do x0. And the output of this other room is probability of y given do x1. And this is the swing or the contrast between these two constants that we are talking and calling causal effect. Then you mimic the condition that you have here. This is nice, and this is a solution. The only trouble with that is that you want to compute from observational data. You cannot run the experiment that always, right? You have problems of costs. Some of these trials cost dozens of millions of dollars. But even if you have money, you have problem of technical feasibility. Sometimes, I will show an example about cholesterol, that I would like to check the effect of cholesterol in heart attack. But you cannot open the patient, throw a dice with 200 levels, and randomize and decide a cholesterol level for it. It's technically infeasible, even if you have the whole money of the world. Then this is a challenge, and this is a valid question. Effect of cholesterol in heart attack. Sure, it's important. And I think those are the reasons. What else? Yeah, this is about it. Then the main question is, what's the relationship between z, x, w, and y with y given to x? And this is a question. Yeah, this is one. And another one, is y given to x the same of y given x? Then you already know that not. You'd already said I'm implicitly saying, but for sure not. And classical example that I like that's kind of funny for me is about the rooster. You get the correlation between the rooster and the sun rising, and it's a strong correlation related to this y and x. There is even that signature of temporal precedence. The rooster crowing usually happens before the sun rising. At the 80s, it's in Yuda's book, but at the 80s, people believed that probability raising and temporal precedence was the key for causality. This is clearly not the case. If you wake up the rooster a little bit before, at 3 a.m., for example, and make it to crow, the sun will not rise for sure. Then these numbers are different, right? These two numbers are different. Then you kind of this pops out the difference. What I would like to do now is to show then how can you compute really the effect of the intervention and observational data. And I will try to contrast a query that we are used to, probability of evidence, with the causal query. The probability of evidence, the way that I see that is the following. You're trying to get probability. This is a classical example: season, spring, rain, wetness, and slippery. And I'm trying to compute the probability of wet given sprinkler is equal to 1. The sprinkler is on. The way that I see that is sprinkler propagate evidence and change the likelihood of wet through this path here. And also sprinkler on change the likelihood of season, that in turn change the likelihood of rain, that then also change the likelihood of wetness. Then you have these two paths, P1 and P2, that accounts for how sprinkler and wet are moving, how they are moving. What we want is the probability of wet given do sprinkler. And somehow we are trying to convey, but you want to cut the influence. There is an external agent. Someone came to the system and perturbed. Sprinkler is not turning on in a dry season as usual, or turning less like in a humid season. But now someone came outside, autonomous, and put their hands in the system. Then they cut this edge here. And what we want is how sprinkler wet changes with sprinkler. That is accounted by this path P1 here. This is our goal. And turns out that there is an expression for that. If you get the regular factorization that you have, the causal one, and then you have probability of season, probability of sprinkler given season, and the family decomposition, as Yuda said, you just wipe out or remove the factor that was related to sprinkler given season. And this is kind of the semantics of the atomic intervention. That is the basic one that we are trying to understand. Then, this is nice and leads us to a more general way to do that, besides one sprinkler, that it calls the truncated product. Important, don't try to parse now, but the truncated, I need to mention the truncated is also, there is another names. It's manipulation theorem or geocomputation. They are learning in different contexts. They're slightly different semantics. I'm just collapsing everything here. I think it's useful for us. And it basically tries to relate this real world, or the P, with the alternative world, or the P prime. And the way to, let me read it. The distribution generated by intervention do X in a Markovian model M so far is given by the truncated product, and you have two pieces. The left-hand side is giving the intervention distribution in the alternative world. And you have probability of V1, V2, Vn given do X. It's another distribution, as you said. And this will be equal to some distribution over the real world, or the one that is happening now, not this alternative, that factorize in this way. The probability of Vi given the parents of Y, given the family. This is nice. There is a trick here, or this is generalization. A lot of sprinklers. You want to remove the sprinklers, or the guys that we are doing the intervention. Then I'm removing from the products the families that are not in X. X is the do X, or the variables that you put our hands on. Then you just remove that. This is just a bunch of sprinklers in our case. This is nice. And this is the intuition that you got so far. Note something important. This relies strongly in the graph structure, because you rely on the parents of the nodes Vi to be able to make something. And one important point. I'm pointing as corollary here, because this is related to also the theorem that you have from Pearl and Verma 91. But some people don't like higher. This is warning if you are reading the literature. But some people don't like layer 3. Then you could take that as a definition. This could be taken as a definition of intervention, and this will be fine too if you are interested just in answering interventional queries. This is nice. I would like to make the point, no free lunch. It's very tempting to believe that this product here is the Bayesian product. When I get reviews, this makes me unhappy, and I have to discuss, sorry for externalizing, but it's very tempting to believe that, and this is not the case. As he mentioned Cartwright, he said no cause in, no cause out. It seems that there is no causal assumptions, or some people just reading fast, where are the causal assumptions here? This truncated product is loaded with causal assumptions. And the assumptions, I like this definition, but I like this one more. And this is an equivalence result that he gives as homework in a second to prove that they are equivalent, and it's very nice. Let's just recall the notation. The notation said that you have observation distribution P of V. You have an experimental distribution probability of V given to X. And you have something called a P star. This is the collection of observational and intervention distribution together. And then a causal Bayesian network is defined the following way. A DAG G is called a causal Bayesian network, compatible, and it's a formal sense for people that knows Bayesian network. This has a meaning, compatible with P star, if and only if 3 conditions hold for every intervention distribution P of V given to X. The conditions are the following. Number 1, the intervention distribution P of V given to X have to be Markov relative to G. For Bayesian network, people understand what this means. If it's not Bayesian, there is some notion of you can map the distribution in the graph, and you preserve some properties of the distribution. It's some agreement. It's a technical notion, but it's fine. Let's not be nervous because of that. This is Markov. Important point, if you consider the null intervention, X is equal to 0, this is the same probability of V, the observation distribution, is Markov relative to G. That is nice because this is the definition of Bayesian network itself. Then it's kind of popping out that you have more things than just the definition of Bayesian network. Just one piece is related to the Bayesian network. The second property is kind of technical, but it's important. It's called effectiveness. It says the following. Probability of V given to X is equal to 1 for all Vi that is inside X. Meaning, if you put our hands in the system and we decide to set the sprinkler is equal to 1, all mass of probability will be shifted there. There is no other option. And this is the contrast to the filtering. And this is equal to 1, called effectiveness. That's it for this one. There are other technical details, and the third one is the Vi given the parents in the intervention distribution to X is equal to Vi given the parents. For all guys of all variables, Vi's that are not related to the intervention. Meaning, if you go and put our hands in the system, in the sprinkler, the distributions under this intervention of the other variables will keep intact, will not change. This is very clear in the third layer, but in the second layer you need this thing. This is the mirror in the second layer. And this is called modularity or autonomy. It's interesting. There is a note here for people that is used to Bayesian network. This is a declarative condition. We are showing what we want from the Bayesian network. There is a constructive definition. It seems that people like constructions. In the Bayesian network, what we have in terms of constructions, the classical one, is Vi is independence of the non-descendants of I given the parents. This is the basic way that you construct Bayesian network, which means you try to shield Vi from the other non-descendants, given the parents will shield the Vi from the other variables. Here we have some sort of shielding, interventional shielding, that says the parents are shielding Vi from intervention in all other nodes in the network. Then this will give you a construction encoding this kind of constraint. And this is the definition of causal Bayesian network. I think it's very, very nice definition. And what is important, I don't like, this is a side note. Some people, the way to test if you have a causal Bayesian network is to check if there is a variable that is a parent of two variables in the network, this variable should be in. And this will appear later, and we will discuss about that. But if you are used to Bayesian network, usually, yeah, this will make some sense. But let me move on. Given that you understand semantics of intervention, how to use the truncated, and also the assumptions that are behind causal Bayesian networks, I would like to talk a little bit about the backdoor criterion. That is when you cannot measure the parents of the variables that you are interested in. Because you rely strongly on having the parents. And sometimes this is not possible. And usually it's not possible. By the way, this is one of the reasons that the FDA, when it can, he will run the experiment. Because he's trying to avoid to have to elicitate or say who are the parents. He's just saying, oh, let me put the coin as being the parent of this variable. And we know that it is not always possible. Then he called that, this is our picture, the question is if season is latent, is the effect still computable? Can you still get the effect? Our original graph was this one, and you are trying to get P of P1. You have this factorization. I said that you remove the product sprinkler given season. If you do a little bit of algebra, that will pop out what I'm trying to say. This is equal to probability of wet given sprinkler season multiplied by probability of season. And this guy is called adjustment for direct causes. It's a known way. You just adjust for the direct causes. It's kind of different kind of conditioning. It's not conditioning exactly, because if you do conditioning, you have, if I just condition on season, you have season given sprinkler here. It's a different kind of transformation. Then this is adjustment for direct causes, and you rely on having the season here to be able to do this adjustment. But what if you have, instead of season, you have a U node? As he said, oh, this is the background variables or the exogenous variables. What if this is latent? Then you cannot condition, and you still have this path that is not interesting for us, or this is the spurious path. It's going to the back door from an edge that is coming here, and not a direct or a causal edge that you are trying to capture. Then how can you get that? I'm not sure if it should be clear, it's kind of intuitive, but if you condition on rain and do the same kind of adjustment, the same kind of formula and just replace with rain, you get the same answer. And this kind of more general adjustment, you're doing the adjustment for rain. Then you can replace, you don't have the U, but you have rain, then you still have an adjustment. And this leads us to a more general criterion that is called the backdoor. That is related to this problem of confounding, or these variables that are creating spurious path. More generally, what we want is find the effect of x and y given to x, given measurements of auxiliary variables z1, z2, zk. You just can measure some of them, and then you have a graph like that. And then how can you do that? Originally, what you do, you got the parents, z3 and z4, and you adjust for that. But then now assume that you cannot measure that, and you cannot measure that, you cannot measure z1 and z3. Then you have trouble, because if you have paths going through this guy, not going through this edge x, z6, and y, but going through the back door here. Then, if you think a little bit, you see that if you choose z4 and z2, they will be sufficient for adjustment. They will be admissible. This is another backdoor admissible. Then you'll be closing the backdoor paths. And this is kind of interesting problem, because people in empirical science, they struggle with this. They want to adjust, but they don't know which variables to pick. And this gives you a graphical way to say what we are doing and which one you should pick. The tricky question, suppose now that you choose Z4, would be sufficient for adjustment. This is just for practicing. Yeah, I don't have much time. Then the answer for the practicing, note that you have this path here. Z1 and Z2 are pointing to Z4. then this is a collider. Then I have this path, X, Z3, Z3, Z1, Z1, Z4, 4, 2, 2, 5, and 5, 1. Then you have this path open here. Then if I just choose Z4, instead in together of Z3 or Z2, I will be opening this path, and then it will not be sufficient for adjustment. It will be there, the confounding. More generally, what this criterion gives us, you have a graph, and it's a two-step procedure that you should do. You have the original graph, you should change the graph somehow. And the change that you do in the graph to pop out what are these spurious paths, you remove the outgoing edge from X to all other variables, in this case, Z6. Then the variation that is happening between X and Y, they are happening because the spurious paths. Then what I check, the two-step. First step, change the graph in this way. We call this graph GX sub underlining X. And then you have this one here. Yeah, I have the label. And now you check if you have independence given some set Z between X and Y. In this case, you could pick this set, for example, Z1 and Z4. And then you have independence. X is independent of Y given Z in this special graph. And this is the algorithmic way that you have to check backdoor or admissibility. A little bit dry. And the formula that you have, or how you use that, there is this formula, there's the adjustment that is known. This is the justification. I have the semantics. Now you understand how to pick the variables. This have Y given to X. This adjustment Y given X and Z multiplied by just the prior of Z, the marginal of Z. And recall, you are used to Y given X will be just Y given X and Z multiplied by Z given X. It's a different, completely different animal or transformation here. Then this is a very nice criterion. And you can go beyond. The question, is it true that in reality this is the only way that you can get causal effects? So far until I think early 90s, this was the way. Even though they didn't know how to pick the variables, but this was the way, do adjustment. But is there any other way that you can get what we want in this alternative reality, alternative world, given that you collect passive data? And this is the challenge. Let me read the goal. We want to find the effect of smoking on cancer, going back to Fisher, probability of C given to S, given measurements of auxiliary variables T, that will be tar, that is the tar deposits on the lung, and when latent variables confound the relationship between smoking and cancer. Then this is the graph. I'm putting these dashed arrows. That means that they are latent. This is the convention. And then you have this genotype that is unobserved. This is the argument. And then you have smoking to tar, tar to cancer. And you can see if you try to use the backdoor criterion, let's remove the edge from smoking to tar. Then there is no edge here. And then you check, is there any set that I can condition and making smoking and cancer independent? The only that would exist is the one that is genotype, that is passing through this bidirected arrow here. But I cannot condition on it because this is unobserved. Then what should I do? Right? Then it seems that there is no adjustment. It's not possible to adjust. Then this is the motivation. The hint that I will give, what about computing the effect of smoking on tar? I have smoking on tar. Is it possible to compute this effect? Let's try to use the backdoor. If we remove the edge from smoking to tar, smoking is independent of tar. It is. There is this path. The other path, the only remaining path is this smoking genotype to cancer, but this note that this is a collider. There is this converging arrows here. Then they are independent. Then it turns out that in this case, the null set is sufficient for backdoor adjustment, or for adjustment. This is nice. Probability of T given to S is equal to the probability of T given S. Nice. Second hint. Can you compute the effect of tar on cancer? Let's try to do the backdoor again. You remove this edge from tar to cancer, here. Then you check, is tar independent of cancer? It's not. There is this path here, tar, smoking genotype of cancer. But you can see that if you condition smoking is sufficient for adjustment. Then I can do a second kind of adjustment over smoking. Then C given to T is equal to the sum probability of smoking, probability of C, comma T, S, smoking, multiplied by the prior of smoking. This is another adjustment that you can get. That you should do. Then the question, from here, how can I get the effect? There is some issues about transitivity in causality. It's not necessarily you don't have this property. The question if you are doing some kind of convolution, can I combine these two guys and get the effect? There is no way that you can answer that now, but this is the motivation to go to the third or the fourth tool that is known the do calculus, that generalize this problem or the techniques that you have of adjustment, backdoor, and so on. This is very nice. Warning, don't try to parse that, but this is the calculus, or causal calculus, another name. And how you read this thing. Let me just read the first statement. The following transformations are valid for every intervention distribution generated by a structural causal model. And then you have this rule, 1, 2, and 3. How you parse, 1, 2, and 3. And you have some condition in green. If the condition in green holds, then some equality will hold. You have these other equalities. Let's pick rule number 2. This is basically, this condition here, believe me, but you can check later. This is basically the backdoor condition. This is if the backdoor condition holds, if you can remove something from Z underline here in some special graph, then this equality will hold. What this equality is saying, I just show here in yellow, the only difference between the left-hand side and the right-hand side. The left-hand side, I have a do Z. In the right-hand side, I have a Z. Then I'm exchanging do Z for CZ, observing Z. And this is the backdoor condition, or the second rule. The second rule is a little bit more general, but essentially the backdoor condition in rule number 2. What about, I don't expect to understand in all details the do calculus, because in class you spend 1 week on this kind of results, on chapter 3, but I try to give the feeling of how it helps our problems, or this is as a tool. Rule number 1, ignoring observations. This is basically, note that you have let's ignore that for now. If this condition holds, I have a Z here and I don't have a Z here. This is basically this separation. It's saying that this separation also holds in the intervention space or the intervention distributions. It's very nice because you can acquire our old friend tool to use here also in the intervention space. And then you have this rule number 3 that is adding or ignoring actions, that you have a do Z here and you don't have do Z here. Then you can remove the do Z altogether. The Z doesn't matter for the likelihood of Y. It's a little bit tricky, the condition, but the intuition is if Z is non-ancestor of Y, usually you'll be able to remove it. Then this is the do calculus. And basically we are checking these separations in these special graphs, the transformation of the graph to check if it holds and if you can exploit this equality. Then let's go back to our problem. That you have smoking, tar, and cancer, and then you have the genotype, and then you have the tar in the middle. Our target expression is C given to S, and then don't parse, but then you have a derivation in do calculus. And the derivation is basically, we are augmenting probability, you already know that, and you have these rules, and then you keep applying the rules, and this is the graphs that I'm saying in green, that are in the previous slides. You keep applying and then massaging the expression, as you say, and then you went to an expression when you have C given to S from the alternative reality that has the do to an expression that there is no do. Everything is white. Then you are re-expressing this is our syntactic target. You want to re-express something from do to no do, everything white. And then you can make the claim. Then this is nice. You didn't want me to put this slide, but I couldn't resist this one in particular. But don't quit if you don't like this slide. But for someone who's a little bit more in causality, this is what we do usually. This is the way that you see this problem that we are trying to pass the intuition. I don't read the problem, but this is the decision problem. And the question, I have 2 models, M1 and M2. 2 models in layer 3. Could be in layer 2, but let's be more general and broad, open-minded. You have layer 3, M1 and M2. If the 2 models entail P of V, P1 of V is equal to P2 of V, the 2 models agree in the observational distribution, you would like them to agree in the query, Y given to X. Y given to X1 should be equal to Y given to X2. This would be implied here. It's an entailment notion, that you can extract the knowledge from our assumptions that are encoded in the graph, that are compatible with this model, or encoded in the graph, and then if they agree in the distribution, they should agree. What this is a miracle, or calling something like gift of gods, I consider this one, that you don't need the details, that he said, oh, you never get the functions. You never get of P of U. This is the beauty of this thing. You don't need it in this case. And this is a problem that's known an identifiability problem that is like, I don't know, 30 years or 50 years open and was closed, I don't know, 8 years ago. And it's very nice. It's a miracle. You don't need F of P of U, but you want to talk about that. And this is the formal way. Don't quit. This we are trying to find a function. You have a G, and you are trying to function from G or P of V to P of Y given to X. This is the technical. I have 15. Then this is nice, and then this identifiability problem was solved. I like to, but it's not always possible. It's not. Sometimes it's non-identifiable. This is not the smallest, but the second smallest graph that you have a non-identifiability. It means that Y given to X, we cannot get it. The answer will be no. There are two models. There exist two models that will agree in the observation distribution and disagree in the query. Then what can you do? And let me put a face to this graph. Let me just put some labels here. The X could be cholesterol level, Y could be heart attack, and Z could be diet. And if you try to check if you try to check what is Y given to X, the answer will be no. You cannot get it. Then is it possible to get? Someone could say more, don't want the graph, they say, oh, go to randomized experiments, try to do. As I said, impossible. You cannot open the patient, throw a die with 200 faces, and decide the cholesterol level of the person. You can technically infeasible to do that. Then identifiability with the assumption that this is basically the science that you have, say no, you cannot get it. Then is it possible to get? Somehow it seems a relevant question, right? At least to me. You might have something called experimental study. I cannot randomize cholesterol, but it's not difficult to randomize diet. I can give, I don't know, Atkins to one group and no Atkins to another. And then I can randomize diet. And the question is, this new piece of experimental data, of evidence, can help in this exercise. It turns out to be true that it's the case. And the Y given to X now become X and Y given to Z divided by X given to Z. This is the expression. Note here that you have a different syntactic goal in this problem. In the original problem identifiability that I just talked, you are trying to move from do X to no do at all, from yellow to the white. And here you are trying to move from do X to re-express into the syntactic in terms of do Z. This is our goal. This is nice. Yeah, and what we're trying to do here, don't quit, but you're just trying to find a function here from this G, P of V, and P of V given to Z to the P of Y given to X. This is our goal at the end. This is nice. And what I'm talking here, or the culmination, or originally what we believed that the do calculus was capable, one of the capabilities, was about policy evaluation. And Yuda doesn't like the name, but this problem is also called in some fields, I don't know if it's called in some fields called internal validity. And this is the problem that the do calculus was solving. Let me just put a summary of what I talked of the results about policy evaluation or internal validity. You have estimability of any expression in the form Y, Z, and X, they are vectors. Y given to X and Z can be determined given any causal graph G containing measured and unmeasured variables. They're kind of more general here with latent variables, or if you know semi-Markovian models, but it doesn't matter. And then you have if Q is estimable, if I can get the quantity, then estimable can derive in polynomial time. There is an algorithm to find this formula, or the estimate. And the algorithm is complete. This is good. And the causal calculus is complete for this task, which means that if you want to go through the algebra and try to apply the derivation to calculus, if you try hard and you try all possibilities, and if you don't get, it means that this is impossible. No other method will be able to get this kind of guarantee or the convergence or the consistency that you want. I would like to move now. I would like to move now for transportability. That is, in policy evaluation, we are talking about one population, and now we would like something a little bit more general. This is when you have multiple populations. And it's kind of a problem that was lingering, and when you we read 6 months or 1 year of literature, you kind of can see that they're kind of struggling trying to express. You don't have a formalization even of the problem because they didn't have language, and this is very nice and lucky. And in the empirical assessment in general, social science and stats, right, in general, even that is given methodology for them. And this is called about, we call generalizability among populations. Oh, there is a typo here. And this is transportability. And the question, is it possible to predict the effect of X and Y in a certain population pi star? Now you have this entity called population that you didn't have, population pi star. No experiments can be conducted there. It's more a relaxed version. Using experimental data learned from a different population pi. Then you have two populations, source and target. The source is pi, the target is pi star. I can run experiments in the source, and I would like to know if I can make the claim on the target. This is the problem. It's related to generalization. And I just just quotes this to give context. This problem is known as other science, as I said, and there are different names for the transportability family. External validity, meta-analysis, and others. And this is a quote by Cox, a famous statistician, in his book of 58. He asked, extrapolation across studies requires some understandings of the reasons for the differences. This is kind of anecdotal. It's a nice quote and insightful. And he's saying basically you need to understand about what are the differences. And what's our goal is to try to pinpoint, formalize, and exploit that as much as possible. Because this is kind of a very general, broad way to put the problem. Let me just read another one, my last quote. By external validity, this is by Cook and Campbell, the fathers of quasi-experimental design, the Black Book, and also with Chadish, saying external validity asks the question of generalizability. To what population, settings, treatment variables, and measurement variables can this effect be generalized? This is the question. There's another by Mansky that I will skip because I don't have much time. It's from social science, an important person there that is concerned about this problem. And the metaphor that I have in mind when I think about this problem is the following. Moving from the lab to the real world. We have some place called the lab that is very dear for us, and in the lab we can put our hands on, do experiments, change things, do whatever you want, because you're in the lab, you're at home, right? And then you have about the relationship between the lab and reality. And the relationship could be, one hypothesis for the scientists that we're trying to put ourselves in their shoes is reality could be the same of the lab. This is H1. They could be the same. Then everything that I run in the lab and the results, the experimental results that I get there, I just move to reality. Because by assumption, they are the same. Then we call everything is assumed to be the same, is trivially transportable. This is easy case. This is the dream scenario. And the other hypothesis is the lab and reality, they are completely different. The lab is the peaceful place, you can do whatever you want. Reality is a chaos. Then how can I move from one to another? Impossible, right? It's impossible. The answer is easy, it's impossible. Impossible in the sense that you cannot provide guarantees. And we are looking for things like central limit theorem or formal guarantees of what we are doing, not doing some kind of ad hoc. The answer is simple. Everything is assumed to be different, not transportable. Then this is kind of the stage or how you see literature so far, and in the quotes that I gave, or they assume the same or they assume completely different. And some kind of a little bit naive. Everything is not the same always, and everything is not different. I need some water. But and then you have this whole spectrum between these two extremes. And the classical example is about monkeys or mice. You run experiments in mice. You run experiments in mice, and you would like to transfer to the monkeys, and you would like to transport to human beings. You know that the coronary or the digestive system of monkeys is really similar to the human beings. Then you can just get the experiment and some kind of speculate and move to the human beings. But what about the cognitive system? The cognitive system of the mice. You know that you cannot move conclusions from there. Then you have this kind of qualitative coarse knowledge about how reality is. And the lab, what I'm talking here, labs usually is called setting, domain, population, or study. This is just a metaphor for this kind of blocks. And I would like to show what is in between that, because I'm talking a very metaphorical and high-level way, and I would like to give a face, or put a face on this thing. And the motivational questions, what can experiments in LA, that you live there, tell us about New York City? And you have this kind of special kind of causal graph, or the overlapping of two graphs. X is an intervention or an action, a decision, if the guy is taking the drug or not. You have a Y outcome, survival after 3 years of taking the cancer drug. This is the outcome. And you have Z, that is age distribution. The age between LA and New York is different. LA population is younger than New York. This affects these relationships. Like Z to X, for example. Yeah, this affects the relation. Let me cut here. And you have a source pi. You have a source pi, and the target is pi star, New York, LA, and New York. What you have, in the source, you can conduct experimental study in LA. Then this is just the passive distribution, x, y, and z, but the experimental study is y given to x and z. Then you have the effect of x on y for each age group, what is very nice, and you expend a lot of money because this is expensive. Then you try to go to New York. What you have in New York, Mayor Bloomberg just left, but he doesn't even allow people to drink sodas in big cups. Then he doesn't want to allow the population to be submitted to this kind of treatment that can be very harmful. Then what you can do in New York, you can collect census data, or basically sample in a standard way. Then you have the observational distribution, P star of x, y, and z. As a consequence of this yellow edge is marking that, I didn't mention that, but it's marking that in the structural model, in the third layer, there is some differences that is making this population to differ, to have a different distribution. Then this is the consequence. The distribution is that P star of z is different than P of z. This is good. And the question that we want to ask you, what's the effect of x and y in pi star in New York? How can you get that? Turns out that for perhaps 200 years or 250 years, I don't know the date precisely, but demographers do this kind of adjustment or do some sort of combination or mixture, a very delicate mixture. You have y given to x and z from the source, and you combine or reweight by the prior distribution over z, P star of z. The only problem with their formula is that they don't know why this works or under which condition this is true. For this example that I plot here, this is true. But you can change a little bit, you see, and it will no longer be true. Then we would like to amplify that, amplify the intuition that these guys had. You call this the transport formula. There's some sort of mapping from what you have to what you want. As I said, it depends on the story. Transport formula depends on the story. This is the graph that I showed before. I just added some bidirected to make it more fun. If you don't have bidirected, nothing, it's easy, a lot of things. And then you have this adjustment here. Now the question, suppose that the data is not coming from this guy, but the data is coming from this guy here. Now you no longer have age, that is the z, but you have some proxy for age. That could be language skills. Perhaps the society in New York is more advanced, and the kids will learn language earlier. It's a possibility. Then, what will be the adjustment there? Or what will be the transport formula? What will be y given to x and pi star? It's almost obvious, but I will just go because I don't have much time. This will be not this one, not a, but it will be y given to x, the same. The intuition, you can see that z has no relation with the effect of x and y. For the drug, it doesn't matter when the person got the language skills or not. Even though that's a proxy, it's not the kind of thing that it matters to the treatment. Then it's the same, and this adjustment will be wrong, the ones that they used for 200 years. The question, you can go more sophisticated or a little bit more subtle. You have someone in between x and y. It's a biomarker. It's sitting between the treatment and the outcome. And you ask, what will be the transport formula? Will be this one. I like to think of this one as a backdoor for the external validity, because it looks like the backdoor. Will be this one or this other one. And it will be neither this, neither A nor B, but it will be a completely different or a different adjustment. Then you adjust by the z given x. Then it's a pictorial way or a nice way that shows that depending on the assumptions that you have a different sort of formula or way to combine your data in this special or delicate way. Let me just skip that. And then you have analogous results saying that you can reduce for calculus, you have a syntactic goal. I'll not read that, but basically we want to go to expression. Instead of removing the do x altogether or moving from do x to do z, you want to separate the do x from a s node. That is this is bad. This is the box with the arrow, the yellow arrow. Then you have a different syntactic goal. Some people don't like to go through the calculus. I think it's nice, but then you have an algorithm. The algorithm will input some graph, and be any crazy graph following these semantics, and the graph will give the answer for the decision problem. Is transportable or no? Yes or no? And in the case of yes, they will give the transport formula. And the transport formula is this adjustment. You are picking the green from the source and the red from the target. This is the goal. There is completeness. And Yeah, there are graphical criterions also. I don't have time, but you can spot in the graph. You will talk in other instance, but you spot the graph and you know it's transport. There's a signature or some sort of forbidden graph structures. It's like K5 or K33, if you're talking about graph theory, if you understand. But let me just, now my last or second last one, this is what we are working on, or more generally, the goal is the following of this picture. You have some target or the dream, what you're dreaming now. You have this target that will be the US. And you have 8 different locations, or 8 different hospitals or cities. You have, I don't know, LA, New York, Boston, and so on, other places in the US. And each place has a different population, a different structure of the population that is encoded in these red or yellow edges. And also they have different experimental conditions. They have a completely heterogeneous, the data is coming from completely heterogeneous settings. Now, go in some formal sense, you would like to combine this guy and get strength. You would like to guarantee consistency, and you also would like to get power, or statistical way to exploit the maximum as possible from your sample. Then this is the dream, or what we're working on the last 3 years. We're working, trying to do that, or solve this problem. Let me just give you the summary of the transportability results that we have so far. Non-parametric transportability of experimental results from multiple environments and other variations can be determined provided that you have a selection diagram that is encoding these commonalities and difference in qualitative layer 3 things that are needed. When transportability is feasible, the transport formula can be derived in polynomial type. The algorithm is complete, and the causal calculus is also complete for that if you want to play with the calculus. Then that's it. I will pass the ball to Yuda.
I'm glad that we still have an hour and a half, and I'll take most of this time. But those of you who need to leave, I would not be insulted. I understand we're running out of time. Oh, actually, I have 20 minutes. It's a lot that can be accomplished in 20 minutes. Okay, as the third part of the capabilities, I'm going to talk about mediation, because mediation is an exercise that needs the third layer, the counterfactuals. And I'll demonstrate it to you. So there's the only capability that I'm going to demonstrate here, which really needs the counterfactual, even though you're not asking any counterfactual questions. You seem to be asking a very innocent question, such as, I want to decompose effect. First, let's ask ourselves, why do we want to decompose effect? What is, if we do want it, what is the definition of direct and indirect effect? What is the policy implication of that? And when can the direct indirect effect be estimated from either experimental or non-experimental data? And the answer to the first question is that we want to understand how nature works. Okay? If you have direct effect between a certain genetic marker and the outcome, that makes a whole difference in your theory about how nature works. So, in that understanding, however, is a vague word. What does it mean, understanding? Understanding means that we can predict the effect of a richer set of intervention. That is what we really mean by understanding. I understand how TV works, not by turning the knobs and watching the program, but if something goes wrong, I can fix it, okay? Which means I can intervene at a place that is responsible for the malfunction, something that ordinary non-technician cannot do. So the richer the set of intervention that you can apply judiciously indicates the depth of your understanding. But also sometimes legal requirements behooves us to distinguish between direct and indirect effects. For instance, whether employer is guilty of hiring discrimination whole question of discrimination has to do with direct or indirect effect. Is the reason that this lady was not hired her gender or a qualification, even though the gender could play a role in the education and the training of that particular applicant. Okay? So you send people to jail because they are motivated by direct effect, and you exonerate them if the reason that they refuse hiring is only due to lack of qualification. If you send people to jail for something, it means that something is important. Okay. Okay. Now let us deal with the question of what do we do in a case like that? It's a question that I think bothered many good statisticians, scientists. The natural answer is, of course, the habit of adjusting for Z. Right? Even Fisher, when he was asked how to, whether the effect of fertilizer on crop was due to plant sizes or due to something else, he said, let's condition on the intermediate variable that you want to allow for. That's the language he used, that you want to allow for. So condition on it. And it's very reasonable. If you want to keep something fixed, you want to disable this path, being. What you do is you condition on the mediator. That's the way to call it fixed. If you want to hold something fixed, and you don't have any language besides probability theory, you condition on it. That is the curse of the century. And indeed, it's wrong. Because if you have a collider, let's say you have a common cause for Y and Z, okay, conditioning on Z will create a path here. And the reason is, as we said before, that conditioning is just selecting. You select only samples that has a condition Z is equal to 0, is equal to 1, satisfied. So it is a filter. Conditioning is a filter on sample. It is not holding Z fixed. Good. Now that we get that, so what do we do if we don't want to condition? You have a do operator, but do Z. Indeed. This is the definition of control direct effect. It's a difference between the expected value of the outcome under two situations. You hold Z fixed at some level, and then you see the difference between do X, 0, male, do X, 1, female, and don't ask me a question, how can you hold the sex or the gender fixed? Because do is a symbolic operator on the graph. It's not you do something you do physically. Okay, so if you define that to be the direct effect, yes, then the answer is it's solvable. Because as Elias showed in the last slide, every expression that has to do expected value of y given do and given that you see, those expressions can be submitted to do calculus, and the answer is yes or no, which means I can identify it or I cannot identify it. And if I can, I'll give you a formula. But notice that it is, first of all, okay, it is complete, and we have an algorithm to find that one, but notice it is z-dependent. If you hold it at a lower wage or at a lower qualification or high qualification, you're going to get different results here. So you can average over it. The question is, what is the weight? Okay. And there's something else that will behoove us to define it counterfactually instead of interventionally. So the idea was originated by Robbins and Greenland in 1992, but they noticed that this kind, I'll give you the definition soon in a second, and they noticed that it is not identifiable even if you have randomization, randomized experiment. And here is the definition. Okay. The direct effect of X on Y will be defined doubly counterfactually, with a nested counterfactual. It's expected change in Y when we change X from X0 to X1, And for each unit in the population, we keep Z constant. We keep it constant, but at what level? At the level that Z would have had before the change. So now you have a nested counterfactual. One has to do with the Y, and one has to do with the value of Z. But are we scared of nested counterfactual? I said counterfactual is high school algebra. We just solve the equation. So as long as we have a mathematical expression for that, here it is. You keep Z to constant, which is the value that Z would attain had X been X0. You put the value that Z attains as a subscript for another counterfactual, Y had X been X1, and you subtract it. But it's well defined, easily computable if you have all the functions, and the question only remains, is it identifiable if you have only observational data? Robbins and Greener left it because they noticed that it's not identifiable even if you have intervention. Even you can run randomized experiment on X and on Z, you cannot identify that kind of thing. However, if you really believe in the synthesis or in the symbiosis between graphs and counterfactual, one can do some nice mathematics and show that it is identifiable under certain conditions. So here, that's what I'm going to talk about. And the problem is even amplified, aggravated, when you have an indirect effect. Because indirect effect cannot be defined by controlling anything. There's no variable that you can fix in order to disable the direct effect from X to Y. Nothing you can fix to disable that one so that the result that you measure, the correlation you measure, can be attributed to the indirect effect. So what do? You have to define it in the same way, and that definition goes like that. The indirect effect of X on Y is the expected change in Y when you keep X constant. You don't vary. You vary Z. To what level? The level it would have had X changed. Again, doubly counterfactual. Okay. Are we scared of counterfactuals? Not you and I, because we know it's high school algebra. So we just write it down and appeal to the algebra to see if it is identifiable. Okay? And it turns out to be. And also, it is not just hypothetical and metaphysical or introspectional. It has implication on policy. For instance, if you want to find the effect of gender on hiring, if sex discrimination is eliminated. Suppose you invest $5 million in educational program that submit every employer to 5 hours a week to understand that he or she should not discriminate. How valuable is that educational program? You're still left with that one, okay? So you have to evaluate the relative importance of these two paths before you invest in this educational program. It has policy implications. So it's not just metaphysical. Okay. Now that you understand that, here's the answer. It turns out to be, under certain non-confounding condition, this doubly nested counterfactual is identifiable, and here are the results. Look at the results. What can we tell from them? They are all regressional equations. The expected value of Y given something, given Y. The Bayes conditioning bar is sitting there, so you can just estimate it from the data. And something nice about it to know and to watch that the total effect is not equal to the sum of the direct effect and the indirect effect, because we have nonlinearity here. And this is the property of nonlinearity. You disturb that. Okay. What does each represent? The indirect effect represents the fraction of responses explained by mediation, which means the indirect effect by itself can explain what you observe. And this difference stands for the fraction of responses owed to mediation that wouldn't be there had it not been for mediation. Okay? The two different things, sufficient and necessary, that should be computed and reported if you are in that business. And we have complete identification condition. I just want to flex my muscle now and show you what graph can do for you. I'll skip the identification condition. They're all graphical. It tells you under what condition the confounders that might exist there will not hinder your ability to identify. These are the conditions, 2 of them here, and 2 of them are here. The extra condition that one has to watch for is that no member of W, the confounder, is a descendant of X. All the rest are easily done and have been solved before, because look at the requirement here. It says that the causal effect of X on M for specific W be identifiable. Are we scared of that? No, it has the right formula for which we said is a complete algorithm to decide if it is identifiable or not. And if it is identifiable, we have a polynomial time to deliver for generating the estimand. Okay. So this is the conditions for identification. And now I go only to flex my muscle and show you what we can do with graph. You give me a graph, and I'll tell you whether the direct effect is identifiable. And this is called, by the way, natural direct effect. This is doubly counterfactual, okay? Doubly nested counterfactual. It's called natural direct effect and natural indirect effect. And now there is an algorithm that will tell you yes or no. Done. Okay, summary of result and mediation. Ignorability, which you normally hear in the literature, is not required for identifying natural effect. And non-parametric estimability of natural and direct and indirect effect can be determined in polynomial time, giving any causal graph with and without measured and unmeasured variables. Good. I go now to the last capability. It's something relatively new. It's only a few months that we have been working with. Normally, you don't talk about something new in a tutorial. Tutorial, you talk something that has been already baked in the field and proven himself, right? So you would introduce new people to that. Yeah, I need about 5 minutes. Yeah, no, 5 minutes will be perfect timing. So I need extra 5 minutes, or 10 minutes from now. If you need to leave, I won't be insulted. So normally you don't talk about something which is new. However, this missing data exercise should have been done 40 years ago by people who generated the missing data literature, and should have been done easily. Had they have the graphical language. So, and also the reason I said, because we have a paper on that, missing data, in a poster, and also because I believe that the whole missing data literature will change due to this work. Okay. Will totally revamp, because now we have graphs. Fisher didn't have graph. Good. What is the idea? The idea is that missing data is very pervasive in any exercise in data analysis, right? Patients do not always report what they know, and sensors fade and are not reliable. So you have it in every exercise. And it's usually, because of the pervasiveness, it has a huge literature. Each one of our reviewer expressed extreme depth and knowledge in this area. I was surprised. Where do you get in NIP so many reviewers who understand missing data? And it started with Rubin in 1976. It's almost 40 years ago. And it is based on statistical characterization of a problem that is inherently causal. Because there is a reason why data is missing. And the reason makes a difference. So what we need now is a theoretical guidance and the performance guarantee and test of the assumptions. And this is how what graphs contribute here, or not only graphs, but causal analysis, contribute basic change of paradigm. We want to understand what the world will be like for a given missing data procedure to produce expected result. Not the data, the world, reality. And can we tell from the postulated world whether any method can produce bias-free result and how? Okay. There are certain methods which have theoretical impediment to produce bias-free results. And the third, can we tell from data if the world does not work as postulated? That's a statistical implication. And I'll quit that, and I'll talk about, this is very important. To answer this kind of question, you need models of the world, not of the data. Okay? By model of the world, we mean process model, our structural model. Okay? It so happens that reality has no face in most of the statistical literature. Data has probability distribution, but reality doesn't have any face. So let's give it face. Here's the face. This is what you observe. A table where you have a few missing values there, M, a red M. And you're trying to figure out the probability of X and Y and Z. Okay? And these are P of Z star, what you actually observe here with the M, but not of Z. Okay? So Z is missing. That's how we show it. There is a switch there called RZ that turns on and off according to whether X and Y take a certain value. And that switch determines whether Z will be observed, namely Z star is equal to Z, or Z will not be observed, it will be M. That is a picture of reality. Okay? Everyone understand it. I don't have to explain it in this audience. Okay? The question that we have is, can you tell by the structure of this graph whether we can have a unbiased estimate of the probability of Z, or the joint probability of X, Y, and Z. Okay? And this is how we can prove that we can have. You look at the graph. This is your query. You want a P of X, Y, and Z. You look at the graph and say, can I massage my query and manipulate it symbolically so that I will reduce it to terms which are observed? So what is the role of the graph? The graph gives you license to go step by step, for instance, to introduce here RZ is equal to 0, namely the switch says thou shalt observe the correct value of Z. Z star is equal to Z. You see it, RZ? It's separated from Z by X and Y. So it gives me a license to introduce RZ here and continue the derivation. Now I end up with the last term. And the last term tells me everything here is observed. This is Z star. This is RZ is equal to 0. I can see that I don't have an M, but I have a certain value. Good. As I reduce my query to something which is observable. That means that you have a consistent estimate of your desired query. Now the question is, under what queries will enjoy this luxury of being estimable, and what graph will give us a license to do that? And if we assume a graph, whether the graph has testable implication. And the answer is, I'll skip that. It's only for those of you who wants to ask, why graphs? I have another method. Remind me to put this slide on. So now we define recoverability as the ability to estimate things consistency. And non-recoverability means that you have a theoretical impediment. So no matter how smart you are, no matter if you do it with multiple imputation or with a single imputation, if you do it with maximum likelihood or EM, thou will not get the correct results. Okay? So it's very important, practically important, to know if there are theoretical impediments to recoverability from missing data. And then we want testability. Which graphs lend themselves to testing under new condition, that you don't have the data. You have missing data. And it so happens that we have an impossibility theory for some of those questions, some statistical implication of graphs which are of a distribution which is recoverable are not themselves testable. And this is a little strange, peculiar, but this is a result of the theory. So now we are looking, I'm flexing my muscle. We reached a point where you give me a graph, and you give me the reasons for missingness. For variables, for each variable has its own reason for being missing. Like for instance here, I can say this may be a temperature sensor, and this is a pressure sensor, and the pressure sensor determines whether the temperature sensor is on and off, missing or not missing, and vice versa, okay? And so on, you saw all kind of gimmicks, all kind of configuration that looks intriguing to you. Can you tell if it is recoverable or not? And here the answer. Non-recoverable, recoverable, recoverable, non-recoverable, recoverable, recoverable, non-recoverable. The reasons I don't tell you now, but it's all in the theorem. And I can also reason, on some of them I can give you a reasoning. This is called missing almost at random. What happens here? The missingness of y is at random coin. It's not explained or not influenced by any other variables. The missingness of x depends on y. But if you condition on y, then x is independent of its missingness. It's like missing in random. However, y is not always observed. It's partially observed, but it's missing in the random sort of, okay? So you can you don't have it here, you have entanglement. Missingness of y depends on x and so on. Still it's doable. So now we have a theorem that tells you under what condition the graph is recoverable, when it is not recoverable. And the algorithms that come out of that seems to be outperforming the conventional algorithm, because the conventional algorithm only works for MAR, missing at random. That means that only fully observed variables are allowed to explain the reason for missingness. To be recoverable by MAR condition, missingness cannot be explained by a variable which is in itself is already missing. Okay? So, and the territory of not missing at random is a huge territory. That's what we want to conquer and to chart. Here, yeah. And it's all query dependent. Here I ask whether P of x and y is identifiable. But in this one, P of x given y is recoverable. Here, P of x is recoverable, and so on. So it's all query dependent. I think what if we don't have the graph? I'm sure that 95% of you, at least 95% of our reviewer asked that. What if we don't have the graph? And for 25 years, I'm explaining what if we don't have the graph. And I'm sorry that I still have to defend the philosophy of asking, and what if we do have the graph? That this scientific question has merit despite the fact that you don't have the graph now, and give you the insight to everything you do. So let me just answer it here. Constructing the graph requires less knowledge than deciding whether the problem lies in MCAR, MAR, or MNAR. This is a standard literature. Everybody swears by this taxonomy. But to decide on which category your problem lies requires more knowledge than constructing the graph. Why? For one reason is because it requires knowledge about conditional independencies among events in the probability that you don't see. And Graph requires conditional independence among variables. This kind of conditional independence is how people store their knowledge. They don't store the knowledge in terms of numerical values of probabilities. So in that sense, we are ahead. It's easier to construct a graph. Also, understanding what the world should be like for a given procedure to work is a precondition for deciding when models details are not necessary. So if you are trying to make your algorithm graph-free or graph-blind or model-blind to cover a specific situation, you cannot fortify it and with guarantees unless you understand each graph by itself. If the world was, if the reality had the structure of this graph or that graph, you have to understand what happens if you knew the graph before you can answer the question, can I dispose of the graph? So it's a insightful scientific question to answer, even if you don't have the graph. Hypothesizing a reality is extremely important and non-dismissible kind of questions. So please, if you are one among our reviewers, take it into account. And I'm speaking here for a whole school of thoughts that are doing graph-based analysis. We are sick and tired of this kind of question. Thank you. I just want to offend our reviewers, not you. And also, it's easy. That even our reviewer can admit. Knowing whether non-convergence is due to theoretical impediment or whether we are stuck on local optima or some other algorithmic idiosyncrasy, it's important. So if you're doing ML, if you're doing multiple imputation and you don't get the right result, or things get oscillating from one result to another and you don't know what's going on, it's quite possible you have a theoretical impediment, namely that there isn't any estimator that you're looking for. So it has practical importance even tomorrow on your next exercise you're running. And of course, graph unveil when the model is testable. And that calls for a theory of testability, and it's upcoming work. So my conclusion, think nature, not data, not even experiments. Experiments are devised to reveal nature. The target should be reality. Second, think hard, but only once. The rest is mechanizable. Think hard means construct the graph. We really spend time constructing it. But once you construct the graph, all answers should be answerable, all questions should be answerable from the graph. You don't have to re-reason, consult with your peers and debate. Once you agree on a graph, everything should be, is mechanizable, including identification conditions and so on. And speak a language in which the veracity of each assumption can be judged by users or by your peers, and which tells you whether any of those assumptions can be refuted by data. I think, yes, we managed. Thank you for being so attentive. And now, as I promised, I can stay here for the next 4 hours and answer questions. I'm sure you have questions. Elias will be with me, maybe Kartika too. And if we are chased out of this room, we'll go to my room in the hotel and we'll continue until this area is clear. And clear means litmus test of tools. But you are mighty powerful today after this session. Mighty more powerful right now compared with what you were 2 hours ago.
All right, thanks a lot, Elias and Julia. Who wants to go and ask a question? Here we go.
Yeah, I had a question. So a lot of people who are developing algorithms and stuff, they want to, test their algorithms on a batch of test data, and they might, have not really trust their algorithm if if they haven't, validated it yet in that sense.
I
And especially,
didn't get it. Many people have questions about how they can trust the algorithm.
yeah, I mean, I think a lot of people, probably in this community, they want to benchmark it on a certain test set. And then you have certain situations here where you have, like, especially in the third layer with the counterfactuals, even in principle, it's impossible to validate that in a test set of counterfactuals. So then what do you tell people who wouldn't, trust what they're doing without a test set to benchmark?
You lowered your volume at the end, but the end has the crux of the matter.
Yeah.
So I don't really understand the situation. What do you... Testability? Layer 3, yeah. Layer 3 and layer 2 contains many untestable assumptions. And this is something that we have to resign to. When we're talking about causality, we are relying on either experiments or assumptions. Okay. Nice thing about layer 2, that all the assumptions can be verified by experiments, if you can conduct those experiments. Layer 3 has an ingredient that some of the assumptions are not testable even by experiment. Okay? If anyone is worried about it, then take it as a conservative, you can always find bound. Okay? To what degree we are sensitive to those untestable assumptions. But layer 3 conveys the scientific knowledge the way it is communicated among scientists. Scientists communicate in terms of variables that affect each other deterministically, plus some other factors. Okay? They communicate in terms of independencies among the disturbances, namely independencies among the untested factors. So I'm just using layer 3 as a language in which scientists communicate. And we want to capture the scientific knowledge that scientists communicate with and bring it to bear on the question.
Can I add a note?
Yeah, of course.
No, the only note that I already got this question. To get validation in this style of machine learning where you divide sets, right, and you have this, you do that, it doesn't make sense in this setting that you have. Why? Because usually the data that you are dividing is coming from this guy here, from reality. And you're trying to make a claim for a completely different world. Then this doesn't make sense. It doesn't apply for this setting. To do a classical cross-validation or some technique like that.
That's what you asked for cross-validation?
Yeah, for example, it just seems there's a methodological incompatibility between this and what a lot of people would, in machine learning would do.
The normal cross-validation doesn't apply here because everything that we have done and we expose today is infinite sample model. We talk about identifiability, not about estimates. So cross-validation normally you do to when you have a finite sample and you want to cross-validate against another sample taken from the same distribution, right? We have infinite samples here. That's not the question. He said there are questions that in causal reasoning that cannot be answered even if you have infinite samples. You take infinite samples of the rooster crow and the sun, and you find there's a correlation there, and no matter how billions of samples you're going to take, you're not going to get the answer that the rooster crow does not cause the sun to rise. The same correlation comes in and in every day. So what cross-correlation can I do? I measure the rooster for 1 month, and I come up with the conclusion, and I test it on another month. This is not the question here. We are dealing with the problems that even if you have infinitely many samples, you cannot answer.
Right. Looks like we have another eager person here.
All right, next question.
Okay, well, thanks for the talk. It's an extremely interesting framework. So I guess my questions are related to the previous one in that I'm wondering what's this good for, or what should we do? And so I think the previous question is, as machine learning people, what do we do with all this? And I guess I have a related question, which is, as social scientists or health statisticians, what should we do? Because, so there's things out there like, Rubin's causal framework. You've written very interesting things, it's an alternative to your framework. You've written very interesting things about how it doesn't capture everything. But people have used Rubin's framework in thousands and thousands of studies to do causal inference. So what do you see as the goal of this work? Is it to develop new methods, like something that's like propensity score matching but better, or just to explicate what's currently happening?
Yeah, you asked me 3 questions. So I'll give you 3 answers. First of all, Rubin's work is subsumed by this work, because when I give you a graph and I tell you I can compute the potential outcome from the graph, it means that everything that I compute, Rubin's will also compute. Except if you look at the language in which we use to articulate assumptions, that language is different. I articulate assumptions this way. For instance, I say there's no link between Z and W. That's the way I articulate assumptions. Right? Yeah, we'll go to that. Let me finish the 3 questions, and if I forget any, let me know. So that's one difference, very important. Look at the difference, but let's examine it because it's important here. Let's take this example as a working example, as a very concrete one, okay? We have here smoking, cancer, genotype, and tar deposit, W. The way I express my assumption is there is no link between Z and W, which means the rate at which tar accumulates is independent on a genotype. Okay? That's what I assume here. You can refute it if you understand, if you are a lung expert. Okay? But we can communicate. If I were to show you how you need to express it in the potential outcome language, you'll be embarrassed. The way that this simple graph and these 2 assumptions that I have, one is that there's no link between X and Y, the other one is no link between Z and W. If you were to articulate it in the language of potential outcome, namely in terms of ignorability conditions, okay, it will take you 4 lines. None of them is comprehensible by anyone, including Rubin. And I tried it on his. So you choose. If you want to articulate assumptions in the language it's communicable to scientists, or in the language that already prepare most of the work for solution. It's not friendly. You cannot tell if the assumptions are redundant. You cannot tell if they are complete, if this is all you wanted to assume. You cannot tell if any of them implies a certain statistical implication. Okay? That's what I mean by friendly. So one difference is the friendliness of the language. But there's more to that. Okay? It's too elaborate. The other differences are too elaborate. So I'll stick with the language. And that's important because the language, the veracity of your conclusion are equal to the veracity of your assumptions. So if you are in the business of relying on assumption, and every exercise in causal inference relies on some untested assumptions, right? You have to be concerned with the question of how human beings store their scientific knowledge. You cannot have the luxury of saying this is psychology, it's not our business. No, it is your business. And I'm making a claim here that talking about relationship among variables is the language of scientists, not talking about ignorability.